Okay, so a lot of times in probability, you've noticed that we'll have the probability of something is the number of ways that something can happen over the total number in the sample space. So counting becomes an issue when things are complicated. So let's say that what I'm going to do is flip a coin and then roll a standard six-sided die and then roll a four-sided die. I don't think I have room for this branch, but you can get the idea. So first I'm going to flip the coin. So it's either going to be heads or tails. And then after that, I'm going to roll the die. And then for each of these, I'm going to roll that next die. If you count the end of these branches, what you'll get is there were two kind of major branches. So there's two of those. And for each of those, then there were 6 secondary branches. So there's 6 of those. And then for each of those, there were 4. So it's just how many ways can I get a result from the coin? How many ways can I get it from the die? How many from the four-sided die? You just multiply them together and it counts the branches for you. So for example, if you go to a restaurant and you are to pick an appetizer, an entree, and a dessert, some sort of set price menu, you can either have a soup or salad. So the first branch is soup, salad. You can either have chicken. I keep forgetting to add a vegetarian option to these. At some point I did, and then I didn't save it. So you have 1, 2, 3, 4 entree choices. So for each of these branches, you have a branch of 4. And then you pick either ice cream or cheesecake. That's 2. So the number of different meals are 2 appetizers, 4 entrees, 2 desserts. So you just multiply them together because choosing the super salad doesn't affect how you choose your entree. So what if you had to select entrees? I had left this blank to kind of count it out, but so if you count these up, you ought to get 16. So what if we had to select entrees for each of 10 people? There were 10 entrees and 1 of each. So there are just like 10 different, say you ordered box lunches and there are 10 people left. And you've got to give those out. And then the question is sort of how many ways can you hand them out? This is obviously a contrived scenario. I'm just trying to get you to think about a counting process. So you walk up to the first person. So here are their chairs. You walk up to the first person and you give them something. You have 10 choices on that table. You can give them any of them. And then the next person, you go to give them something. You only have 9 choices left. So you have 9 ways to give them something. You go back to the table and now there are 8 choices for how to give them something. And it continues like this. This kind of situation occurs so much in life that this has a name. This is 10 factorial. And the exclamation point is a button on your calculator, which I will show you. I'll show you several buttons today with this counting. So these two are by definition. 0 factorial is 1. 1 factorial is kind of clearly 1 because you start with whatever this number is and you go down to 1. So if it's 7, it goes 7, 6, 5, 4, 3, 2, 1. But if it's 1, you say 1 and you're done. But 0 factorial is defined to be 1. That just makes calculations kind of not break. So a permutation is something like what we did with the meals. But it still would have been a permutation if I'd had, say, 5 people to give those meals to. I still would have had 10 choices for the first person, and then 9, 8, 7, 6. I just wouldn't have done the rest of them because I was only giving meals to 5 people. So I'd still have 5 left on the table. And the way that we sort of calculate this is we say, well, it's 10 factorial, but however many I have left over, these I didn't use, I need to divide by that. So in this case, 5 factorial. And maybe I should have said, maybe you give it to 4 people so that these numbers are different. So you want to divide by however many you have left. The way you determine how many you have left is I started out with 10 and I'm giving away 4. So 10 minus 4 is how many I have left. That's where the 6 came from. So these are called permutations, and this would be written 10p4. So what you do for n p r is you take the n factorial, but you're only picking out n minus r of them. So your number of spots is just r. Sorry, you're left with n minus r of them because you're picking out r, so you divide by this. But this is actually a button in your calculator. So let me show you this done both ways. All right, so you click on math and then you see this probability over here. It's possible, depending on your calculator, that this says PRB. Some calculators only have room for 3 things, 3 letters. So PRB or PROB, in both cases, probability. You see this right here in PR. In CR, we're going to get to that in a minute, and then just factorial by itself. Okay, so first, I'm going to show you 10 factorial divided by 6 factorial. And then I'm going to put 10 math. You have to put the number first, then NPR, then 4. And it's the same number because it's just doing that calculation for you. Okay, so there's the formula. We've already talked through why this works. Key here is that you have n objects and you can't repeat them. So like in the box lunch, you couldn't have given the same lunch to 2 people. That's why it was 10 and then 9. If you could have given 2 the same meal, then it would have been 10, 10, or 8, 8, like that. So you can't repeat. But also order mattered. Because if we had just said, like, for one thing, let me just say that back here with this, which ended up to be 10 factorial, that was also 10 permute, all 10. See, it's the same number. So if I had given this person meal A and then B and then C and then D and then E and then F, then that's different from C, B, D, F, E. Like that, right? It's a different situation. That's why we're counting them out like this. If the question was just how many ways can I choose 10 meals for these 10 people, not accounting for order mattering, like it doesn't matter, I'm going to give each meal to somebody is all that matters. Well, I had 10 on the table. I gave 10 out. There's only one way to do that, right? And it could have been more ways to do it if we are, say, giving it to 4. But because it's just how many ways can I choose for those meals. But we did care about order. That's what makes it a permutation. The situation will be different if I gave different meals to different people than what I did. So in how many ways can horses in a 10-horse race finish first, second, and third? Each of the 10 horses is different. You can't have repetition. They each just get a single place. And order does matter because you care if you win first or if you get third. So it's 10 permute 3, which would be 10 factorial over 7 factorial, because I just have the 3 spots and I have 7 left over. And you can put it in the calculator either way you want, but you don't ever have to write this one if you just do the calculator this way. 10 permute 3 is 720. A combination is where order doesn't matter. You've still got in objects. You still can't have any repetition. But this time you do care what the order is. So it's not 3 horses getting first, second, and third in a race. It's, say, 3 horses getting to go compete somewhere. So you don't care when you were chosen. The thing that happens different here is, let's say that I have 10 horses and 3 get to go to competition. So I start out choosing them just like I did before. I have 10 ways to choose the first horse, 9 ways to choose the second, 8 ways to choose the third. So far, we're at still the NPR, which is 10 factorial over 7 factorial. But this time, so I've got, here are 3 things in my list, say. These are all the same collection. I've counted them separately. 10, 9, 8 counts ABC, it counts BCA, it counts BAC, and I could keep going with that, right? ACB. There's every way that I have to write those in a different order. That's how many times I counted it. And that's true for all sets of 3. So that actually each and every one of these things was counted too many times, and the number of ways it was counted was this. If I know it's ABC, the number of ways that I might have put the first one is 3. The number of ways I then might have put the second one is 2 and 1. So what you get is 10 factorial divided by 7 factorial times 3 factorial. So we're just dividing out the number of times we counted each collection when we did it with order mattering. So we've got n factorial, n minus r factorial, that's the 10 and the 7 still, but then r factorial is how many times I counted each group of r. So that's NCR, which you also saw on your calculator. So how many different simple random samples of size 4 can be obtained from a population whose size is 20? You can't repeat in a sample. Order does not matter. So we have 20, and we're choosing 4. There are 2 ways that, so I'll say choose. Really, the C stands for combinations, but a lot of people do say choose. And you may have seen this in another book as like in choose R, like that. That's the same as this, is the same as this, is the same as this. There are a bunch of different ways people write this. Those all mean combinations, but we often say choose because you're just choosing. So C, you're choosing, it's for combinations. P, for permutations, but you're placing them so that you care about order. If that doesn't work for you, then I sometimes discuss the difference between a committee and having a president, which implies also vice president and whatnot. So if you just pick a committee, nobody cares what order you pick them in. But if you have a president, vice president, treasurer, secretary like that, suddenly people do care what order that was given in. So C for committee and P for president, or C for choose and P for place as just a mnemonic. We used to have to, of course, do these by hand, and if I'm honest, it's actually a lot of fun because things get canceled, but I won't make you do that because you probably won't think it's fun. So 48, 45. If you think you might think it's fun, I'll just show you one time. So 20 factorial over 20 minus 4 factorial, 4 factorial. The first part's kind of for free because that's why we divided by the 16 factorial, was just to have this 4. and then you just kind of, and then multiply those. So then it's like 51 times 85. And anyway, it can be fun to play with, but you certainly don't have to. You can always use your calculator, and I wouldn't try to do it the fun way during an exam. The number of permutations of n objects, where n1 are of one kind and n2 are a second kind and nk are of a kth kind, is n factorial over the product of each of the smaller factorials. So all of these have to add up to n, and what this allows for is repeating. So let's say that you were doing a bouquet, some bouquets, and so you had some number of flowers, but some of them were going to be roses. So however many roses you're going to have, and then however many daisies you're going to have, however many tulips you're going to have. And this is the way that you can place them all. But it doesn't matter if you put the first rose first and the second rose second. So we have to get rid of some of the order mattering, but the order does matter as far as rose, daisy, tulip, and that's what this allows for. So how many different vertical arrangements are there of 10 flags? If 5 are white, 3 are blue, and 2 are red. So 10 factorial, 5 factorial, 3 factorial, 2 factorial. And these, of course, I'll add up to 10. If they didn't, we'd be in trouble. This one actually might be faster to do by hand if you had been practicing that, but 5 factorial, 3 factorial, 2. You might recognize that 2 factorial is just 2, so that you don't actually have to do this. I'm doing the denominator first so I don't have to use parentheses. So then I'm just going to go 10 factorial divided by second negative is the previous answer, 2520. In the Illinois lottery, an urn contains balls from 1 to 52. So there are 52 choices. 6 balls are going to be randomly chosen. We're not putting them back, which means repetition is not allowed. For a $1 bet, the player chooses 2 sets of 6 numbers. To win, all 6 numbers have to match of either ticket, basically. So what's the probability of winning? Okay, so we have 52 numbers. Out of the 52, we are choosing 6 of them. That's the total number of options that you have for these tickets, because order doesn't matter. So 52, choose 6. Okay, so that's the total number of ticket possibilities. You have 2 sets of 2. So the probability that you win is the 2 options you have divided by the total number of options there are. If we not completely simplify this, although we could fairly easily, but approximately 1 in 10 million. Right? Because it's 2 in 20 million roundabout. It's a little bit worse than 1 in 10 million. Oh, it didn't even reduce it for me. So it's 1 in 10,179,260.